Take one cruise control function and put it into three different vehicles. The driver sees the same basic feature in all three cars: set a speed, release the accelerator, and the vehicle maintains that target when conditions allow. But behind that simple behavior, the three vehicles may use different engine controllers, different microcontrollers, different communication configurations, and software supplied by different companies. If the cruise control software is tightly built around every one of those details, one vehicle function can quickly become three different software versions. Then a fourth vehicle arrives, then a new microcontroller, then a new supplier. Then somebody finds a bug. Now the difficult problem is no longer just writing cruise control logic, it is maintaining, integrating, and verifying an expanding family of related software systems. That is much closer to the real engineering reason AUTOSAR was created. In the previous lesson, we defined AUTOSAR as an automotive industry partnership and a family of software standards. Now, the important question is why the industry needed that partnership at all. Automotive electronic control originally developed strongly around individual components and electronic control units, or ECUs. A supplier could receive the requirements for one controller, select hardware, build software around that hardware, and deliver the ECU. For relatively isolated functions, that model can be practical. But vehicle functions stopped behaving like isolated islands. Return to cruise control. To maintain vehicle speed, the function may need a driver's set speed request, current vehicle speed, brake pedal information, propulsion torque capability, transmission state and status information for the instrument cluster. Those pieces of information can originate in different parts of the vehicle. The feature the driver thinks of as one function therefore crosses several software and ECU boundaries. This changes the engineering question. Instead of beginning only with what software should we build inside this ECU, engineers increasingly need to begin with what function must the vehicle provide, what information does that function require, and where should its responsibilities be allocated. AUTOSAR's own explanation of its origin describes this as a movement away from a mainly hardware and component-driven development process toward a more requirement and function-driven process. That shift matters because optimizing each controller separately is not enough when the behavior of the vehicle depends on several controllers working together. Now apply that problem across a complete product line. Vehicle A uses microcontroller A. Vehicle B changes to microcontroller B. Vehicle C uses a different propulsion system. Suppose the application software directly reads CAN controller buffers, accesses timer registers, calls supplier-specific diagnostic functions, and knows exactly how one ECU stores its calibration data. The functional idea may be reusable, but the code is not easily transferable. Every change in hardware or infrastructure can create another branch. One software version becomes several closely related variants. A defect may need to be fixed in each one. Each variation needs integration and testing. Knowledge becomes tied to particular combinations of hardware, software, and suppliers. AUTOSAR refers to reduction of this kind of version proliferation as one of the potential benefits for suppliers. The next pressure was reuse. Communication, diagnostics, operating system services, memory handling, and hardware access are necessary in many automotive ECUs. These capabilities matter enormously, but an OEM does not gain competitive value simply because every project invents an incompatible way to route communication data or store non-volatile information. If each ECU project develops these foundations differently, engineering teams repeatedly solve similar infrastructure problems. The industry therefore had an incentive to standardize selected non-competitive infrastructure so it could focus more engineering effort on the functions that actually differentiate the vehicle. But reuse was not only a technical issue, it was also an organizational issue. A modern automotive software project can involve an OEM, several Tier 1 suppliers, semiconductor manufacturers, basic software vendors, tool vendors, and specialist engineering teams. If every company defines its own interfaces and engineering descriptions, every organizational boundary becomes an integration boundary. Supplier A calls a service one way, supplier B expects another interface. One development tool describes configuration one way, another tool uses another model. The problem becomes larger than any one company. That is an important clue to why AUTOSAR became an industry partnership instead of one manufacturer's proprietary architecture. Initial discussions about the shared challenge began in 2002. By 2003, the AUTOSAR partnership had been initiated, and the basis of what became today's classic platform architecture was being drafted. AUTOSAR's concept and first specifications developed further in 2004, and Classic Platform Release 1.0 followed in 2005. You do not need to memorize every date for an interview. What matters is what those dates represent. Automotive manufacturers and suppliers who normally compete identified an area where solving the problem independently was becoming inefficient. They could still compete on vehicle behavior, calibration, algorithms, performance, and product experience, but selected software architecture, basic system functions, and interfaces could benefit from common rules. That difference is essential. AUTOSAR was not created to make every car behave the same way. It was created to make the software ecosystem underneath those differentiated vehicle functions more structured and interoperable. Several design goals follow directly from that problem. The first is managing complexity. Standardization cannot remove software complexity from a modern vehicle, but modular architecture and defined responsibilities can make that complexity easier to contain. The second is software reuse. If software communicates through defined interfaces instead of being unnecessarily tied to one ECU implementation, parts of it can become easier to reuse across projects or product lines. The third is hardware independence. In the classic platform, application software is separated from much of the hardware-specific infrastructure through the runtime environment and layered basic software. This does not mean hardware becomes irrelevant. A function can still depend on processor performance, memory, peripherals, timing, and safety properties. The goal is to eliminate hardware dependency where the application does not genuinely need it. The fourth is transferability. A functional software component should be easier to allocate within an electrical and electronic architecture when its relationships are described through defined interfaces rather than hidden hardware assumptions. The fifth is scalability. A manufacturer may have small vehicles, premium vehicles, combustion platforms, hybrids, and electric vehicles. Their software resources differ. A configurable architecture makes it more practical to apply common engineering concepts across those product lines. AUTOSAR also targeted maintainability, software upgrades, and updates. A vehicle can remain in service for many years. The software architecture, therefore, has to support continuing correction and evolution rather than being treated as a one-time embedded program that never changes. Quality was another motivation. AUTOSAR argues that greater reuse can increase software maturity because common components are used and tested by more projects and organizations. That does not mean reused software is automatically correct. It still requires proper qualification, configuration, integration, and verification. But rebuilding everything from zero for every ECU does not automatically produce higher quality either. Now look again at our cruise control function. In a tightly coupled design, the application might know a CAN message identifier, a particular timer peripheral, a specific diagnostic API, and the details of one microcontroller. Those dependencies make the function difficult to move. In the architectural direction AUTOSAR promotes, the cruise control function should operate through defined functional interfaces. On the classic platform, application software components sit above the runtime environment, while basic software handles large parts of the standardized infrastructure below. In the classic platform, application software sits above the runtime environment, while basic software handles large parts of the standardized infrastructure below. The application can focus more strongly on the vehicle function. Lower layers can deal with much of the communication, operating system, diagnostic, memory, and hardware-oriented complexity. That does not turn migration into copy and paste. The ECU still needs configuration. Runnables need execution contexts. Signals need mapping. Timing must be analyzed. Memory must be allocated. Diagnostics must be configured. Functional safety and cybersecurity requirements still apply. The integrated ECU still has to be tested. AUTOSAR does not make engineering disappear. It gives the industry a common architectural framework for doing that engineering. There's one more boundary worth remembering. AUTOSAR generally does not try to standardize the internal algorithm that makes one manufacturer's cruise control better than another manufacturer's implementation. The competitive function can remain different. What benefits from common agreement are selected interfaces, software infrastructure, and development descriptions. That leads to the strongest answer you can give when somebody asks why AUTOSAR was created. Don't answer only AUTOSAR was created for standardization. Explain the problem first. Automotive software was becoming increasingly complex and distributed across many ECUs, hardware platforms, suppliers, and vehicle variants. The industry needed more reusable and exchangeable software, clearer integration rules, standardized interfaces, and a shift toward function-oriented system design. Because those challenges crossed company boundaries, manufacturers and suppliers created AUTOSAR as a common automotive software architecture standard. That's why AUTOSAR exists. Subscribe to continue building AUTOSAR from the engineering problem into the architecture that solves it. The next question is more practical. We know why the standard was created, but exactly which engineering problems does AUTOSAR solve inside a real ECU project? That's Lesson 14.